We now move on to the study of solids, which, as you know, have a definite mass, volume, and shape. They come in many different types and are differentiated, first of all, by bonding. There are intermolecular forces involved in some solids. In inorganic compounds, called salts, you have ion-ion interactions. The Coulombic interactions between ions and cations hold the molecule together, where the Coulomb's force is the charge of A times the charge of B times the fundamental charge squared over 4 pi times the permittivity of a vacuum times the dielectric constant of the material times the distance squared. You can have ion-ion forces in molecular solids too, such as oxoanions. Also, molecular compounds can become solids through strong forces such as hydrogen bonding, as found in sugars. However, dipole-dipole interactions are not strong enough to sustain the solid state. Solids bound by intermolecular forces are soluble in polar solvents. They also melt at relatively low temperatures. Next, we have network covalent solids, which are very rare, are defined as an infinite array of covalently bonded atoms. Most commonly, in the Earth's crust, you have silicates, which are compounds made of an infinite array of sp3 hybridized silicon, connected SiO4 tetrahedra. More uncommon, diamond, which is an infinite array of sp3 hybridized carbon. Network covalent solids are insoluble. They can be decomposed in strong acids, but they will not dissolve. Additionally, under high temperatures, they will oxidize. Diamond will eventually go to CO2, but they will not melt. The third type of bonding in solids, which is unique to solids, is called band theory. This is applicable to dense and homogeneous solids, such as metals and semiconductors. In these compounds, all valence electrons are shared between all atoms. This is similar to covalent bonding. You still have one molecular orbital for every one atomic orbital formed, and you still have 2 electrons per each molecular orbital. However, as the number of molecular orbitals increase, the distance between them, called delta E, decreases. In solids, delta E approaches 0 with a large number of orbitals, and indistinguishable bands form. The upper limit of what is known as the valence band in organic chemistry as the HOMO, or the highest occupied molecular orbital. The lower limit of what is called the conduction band is similar to what you know as the LUMO, or the lowest unoccupied molecular orbital. The difference between these two bands, delta E, is called the band gap. There are 3 types broadly of compounds. In conductors, the conduction band overlaps the valence band. The band gap is less than 0 electron volts, therefore there is always conductivity. The electrons can move freely. In insulators, the band gap is greater than 10 electron volts. Therefore, insulators will decompose before conducting. In the middle is a very interesting group of materials called semiconductors. When the band gap is between 0 and 10 electron volts, these materials will conduct, but only under certain conditions. In semiconductors, they will only conduct when an applied external energy is greater than the band gap energy. In states where this is not so, you have an insulating state, which is a logic 0 in your computer. When the applied energy is greater than the band gap, the material will conduct and you have a logic 1 state. Additionally, pure materials do not semiconduct. They must be what is called doped with an impurity. Doping is introducing an impurity at small levels, usually on the parts per million. A p-type semiconductor introduces an electron deficiency in the material. For example, the substitution of boron 2s2 2p1 into silicon 3s2 3p2 introduces a hole because boron has one less electron. In this case, the charge flows from positive to negative. In what is called an n-type semiconductor, an electron excess is introduced. For example, the substitution of nitrogen 2s2 2p3 into the silicon 3s2 3p2, you now have one additional p electron. An electron surplus is introduced in the conduction band. Charge flows from negative to positive. As you saw previously in talking about detectors, you can form a diode in what is called a p-n junction, or a joining of a p-type semiconductor sandwiched with an n-type, which will only allow charge to flow in one direction. Semiconductor bandwidth is related to what they're used for. Very low band gap materials are used as microwave and infrared detectors, and also in radar. Examples would be lead sulfide with a band gap of 0.37 electron volts, and germanium with a band gap of 0.64 electron volts. Materials with low to medium band gaps are used in logic gates in computers and integrated circuits. Most widely used, silicon has a band gap of 1.4 electron volts, and in faster machines, gallium arsenide semiconductors have a band gap of 1.43 electron volts. Slightly higher band gaps in the medium range are used as visible detectors and in lasers. Examples being gallium phosphide at 2.3 electron volts and gallium nitride at 3.4 electron volts. The highest band gap semiconductors are used for ultraviolet detectors and lasers, such as the very rare silicon nitride, Si3N4, at 5 electron volts, and aluminum nitride at 6 electron volts. Materials formed by all three types of bonding can occur in two different forms in nature. You have what is called an amorphous solid, where you have short-range ordering only based on atomic bonding. There is no long-range three-dimensional symmetry, and therefore low overall symmetry. Such materials are common in glasses. They are fragile and low melting. Crystalline solids, on the other hand, are highly symmetric. They have short-range bond order and a long-range three-dimensional order. The ordering is in fact fractal. Symmetry is repeated on each level as the crystal grows. Crystals are based upon the unit cell. Each unit cell has an empirical composition identical to the overall material. Unit cells stack together so that the overall crystal has the same symmetry as the unit cell. Unit cells are based on what is known as the closest packing of spheres, where the sphere is the atom and they're packed as close as possible together. Interestingly, there can only be 7 shapes that can act as unit cells where they both have a close packing of spheres and a fractal relationship. Within these 7 shapes, 14 what are called Bravais lattices are possible. 14 possible point group memberships. Within these 14 possible point groups, there are 230 what are called space groups possible. A space group is essentially fourth dimensional symmetry, a matrix of point groups. Therefore, this means only 230 arrangements are possible for a nearly infinite number of crystalline solids. Within these 7 forms and 14 Bravais lattices, we start with what is known as isometric, or simply cubic, where all 3 sides, A, B, and C, are equal, and all 3 possible angles, alpha, beta, and gamma, are 90 degrees. You have from freshman chemistry the primitive cube, where you have an atom in each corner, the body-centered cube I, where you have an atom in each corner and one in the center, the face-centered cube F, with 1 atom in each corner and 1 on each of the 6 faces. 36 space groups are possible for this. Symmetry is lessened as you move along. The next shape is tetragonal, where A is still equal to B, but is not equal to C, and all the angles are still 90 degrees. You essentially have a rectangle. The only things that are possible in this configuration are a primitive cell or a body-centered cell, but it contributes 68 possible space groups depending on the atoms. More complicated, as symmetry goes down, the orthorhombic group, where none of the sides are now equal, but all of the angles are still 90. You have 4 possible Bravais lattices within the shape: primitive, body-centered, and face-centered, and a new one, base-centered, or C, with an extra atom on top and bottom. Further decreasing relationships, and a monoclinic cell. None of the sides are equal. 2 of the angles equal 90, but the third one does not and can be any angle. Within this shape, you can have a primitive or a base-centered cell, leading to 13 possible space groups. Finally, almost finally, you have triclinic, where none of the sides are the same length and none of the angles are the same. This is difficult to reproduce and can only give a primitive shape, leading to 2 space groups. The other 2 shapes are special cases. You have what is called a hexagonal lattice, where A and B are the same, C is not. Alpha and beta are 90, but gamma is specifically 120 degrees. This too can only give a primitive lattice with 27 space groups. And finally, you have a trigonal configuration. The lengths of all the sides are the same. The angles are equal but do not equal 90. This gives a rhombus or rhombohedral shape with 25 possible space groups. The structure of a crystalline solid can be determined by what is known as X-ray diffraction. To start understanding, think of a unit cell as a cube. This cube can hold an infinite number of planes defined by 3 points. The boundary of the cube is defined by atoms. For chemistry, you know that atoms are bound by electrons. Therefore, some planes will hold electron density. It turns out the electron wave function has a wavelength on the order of the wavelength of an X-ray. In X-ray diffractometry, you have a source and a detector on opposite sides of the sample. Each moves by theta degrees. At most point, the X-rays pass through empty space where there are no electrons. At certain angles of 2 theta, the X-ray encounters electron density and is therefore diffracted to the detector. This behavior is defined by Bragg's law, which says n lambda, the wavelength, is equal to 2d sine theta. In further detail of X-ray diffraction and Bragg's law, n lambda equals 2d sine theta, point by point. Lambda is the wavelength of the X-ray. Generally, this is 1.54 angstroms for what is called copper K alpha radiation. X-rays are produced when high voltage strikes a copper anode. The voltage is so high that a K shell or a 1s electron is ejected from the copper. As these electrons are at the bottom, electrons from much higher fall in to fill the space, and an X-ray is emitted. The alpha signifies that only spin-up electrons are allowed to proceed to the sample, where spin-down electrons are filtered out. N is the harmonic. For any diffraction, any whole number ratio will also diffract. Higher order harmonics are also filtered out. Theta is the diffraction angle, and it is equal to 1/2 of 2 theta, derived from the movement of the detector and the tube. The last variable, the d, is the spacing of parallel planes. As you have seen, X-rays diffract off of planes that contain electron density. Also, as you have seen, unit cells are stacked. Therefore, identical planes are parallel between stacked cells and spaced at a given distance d. X-rays will diffract off of each of these parallel planes. In parallel diffraction, 2 outcomes are possible. You can have constructive interference, which gives a signal, or destructive interference, which removes the signal. These removals of signal are called systematic absences, and they are essential to the study of X-ray diffractometry. Because X-ray diffractometry is based on something called the reciprocal lattice, where once again we think of a unit cell as a cube, with directions defined by A, B, and C. Planes are defined by the letters H, K, and L. These are called the Miller indices. They are the reciprocal of A, B, and C. For example, the 1, 1, 1 plane means you move up 1 in A, over 1 in B, and back 1 in C, and you basically have the diagonal cut of the cube. The 2, 2, 2 plane, however, is defined by moving up 1/2, the reciprocal of 2 in A, 1/2, the reciprocal 2 of B, and back 1/2, which again is the reciprocal of 2 in C. Historically, diffraction patterns were recorded on circular film, which is 2-dimensional from a 3-dimensional cubic array. Essentially, what was produced was an inverted and negative image. Technically, the high level of symmetry of the crystals allows its elements to be projected into an inverted 2D matrix, hence the reciprocal lattice. So it turns out in X-ray diffraction that each diffraction pattern is a unique fingerprint. There are 7 shapes and 14 Bravais lattices, meaning there are only 14 possible X-ray patterns. 270 space groups produce 270 sets of unique systematic absences, giving you 270 sets of possible patterns. Each compound, however, has DHKL appear at different angles. This is because larger elements will produce a larger unit cell. Larger unit cells have larger d spacings for the same Bravais lattice. Larger d spacings appear at lower angles. The lattice geometry can therefore be calculated for each peak as follows. If you have a cubic cell, for each peak, 1 over d squared is equal to h squared plus k squared plus l squared over a squared, where you have a cube, so a equals b equals c. For a tetragonal unit cell, where c is no longer equal to a and b, 1 over d squared is equal to h squared plus k squared over a squared plus l squared over c squared. For a hexagonal unit cell, 1 over d squared is 4/3 h squared plus hk plus k squared over a squared plus l squared over c squared. For orthorhombic, where all 3 sides are different sizes, 1 over d squared is h squared over a squared plus k squared over b squared plus l squared over c squared. For monoclinic, where the angles are also different, 1 over d squared is 1 over sine squared beta h squared over a squared plus k squared sine squared beta over b squared plus l squared over c squared minus 2 times h times l times cosine beta over ac. Trigonal and triclinic are very complicated and won't fit on the slide. The key being, once you have a pattern, you see which of these particular geometries it fits under. Whichever one can solve every peak tells you if the lattice is cubic, tetragonal, hexagonal, orthorhombic, or monoclinic. For non-homogeneous crystalline solids, there are several things to bear in mind. For starters, common ionic crystals. One must remember that the atomic radius of the anion is always much greater than the atomic radius of the cation. Therefore, anions define the lattice points. As you have a packing of spheres, ions are round, lattices are square, therefore there will be gaps existing within the lattice between the anions. The cations fit in these gaps, which are called holes. Holes appear at geometrically regular intervals because the lattice itself is geometrically regular. And therefore every cation is either going to be tetrahedrally or octahedrally coordinated. In molecular solids, such as common sugar, the center of the mass of the molecule is what occupies and defines the lattice point. Therefore, you have extremely large unit cells where all the diffraction peaks show up at very low angles, and you have extremely low melting points because there was little cohesion between the molecules. Finally, we look at the energetics of crystallization. We've already seen bonding, but one thing must be realized. Crystals, as has been stated, are extremely symmetric and ordered. Therefore, the formation of crystals violates entropy. Something called the energy of crystallization must exist for the crystals to exist. This is found by an application of Hess's law. In the simple example, we see the heat of formation of lithium fluoride from lithium metal and a half of lithium gas to be minus 594.1 kilojoules. Hess's law says we can go about making this crystal any way possible, and the sum has to stay the same. So to start with, we rectify phase. We vaporize lithium to the gas phase at 155.2 kilojoules. Additionally, we need only one fluorine, so we split the F2 at half of the 150 kilojoules per mole of the bond energy to get an F. Also, lithium fluoride is ionic. So to ionize lithium metal to lithium plus in the gas state is 520 kilojoules. To ionize a fluorine atom to a fluoride ion in the gas phase is minus 328 kilojoules. So we now have a lithium plus gas and an F minus gas, which will form an LiF solid. That's one more step with an unknown energy, and that is the energy of crystallization. Taking Hess's law, as stated, the heat of formation has to equal the heat of vaporization of lithium plus half the bonding energy of fluorine plus the ionization energy of lithium plus the ionization of fluorine plus this unknown crystallization energy. So minus 594 kilojoules has to equal 155.2 plus half of 150.6 plus 520 minus 328 kilojoules plus the unknown X. You find in this case, lithium fluoride has a crystallization energy of minus 1017 kilojoules. The negative sign is instructive. Energy is gained by having the most efficient arrangement of the ions in the lattice. This more than offsets the decrease in entropy by creating order. Finally, one last look at ionic solids. Obviously, an ionic solid such as sodium chloride, a positive sodium attracts a negative chlorine, which attracts a positive sodium, in an alternating pattern of anions and cations. There is therefore a net attractive force. Geometrically, if you look at a sodium ion, it is octahedrally coordinated and has 6 chloride ions as a nearest neighbor. In the next shell, there will be 12 sodium ions, followed by 8 chloride ions, followed by 6 sodium ions, followed by 24 chloride ions, followed by 24 sodium ions, and this will keep increasing to infinity. The net energy felt by our original sodium ion, where R0 is the initial Na plus Cl minus difference, is essentially Coulombic. E squared over 4 pi epsilon 0 times minus 6 for the 6 chlorides over R0 plus 12 over radical 2 R0 for the 12 sodium nearest neighbors minus 8 over radical 3 R0 for the next 8 chlorides plus 6 over radical 4 R0 for the 6 sodiums minus 24 over radical 5 R0 plus 24 over radical 6 R0, and again the series goes on and on and on. You will notice that inside the square brackets are a series of constants that are geometrically determined divided by R0. These can be summed up by the letter M, the Madelung constant, which is the sum of all the net forces felt by any particular ion. So therefore, the Coulombic interactions on any given ion are going to be the fundamental star charge squared times m, the Madelung constant, of all of the nearest and next nearest neighbors over 4 pi epsilon 0. So this concludes the studies of liquids and solids, which are related by intermolecular forces and geometric patterns.